Alright, so we have an algorithm and we're going to count the flops. So flops are floating point operations and we're going to count them. So if we just go through real quick and just go through this line by line, I think that'll be quicker. So let's see, I'll refer to these as lines 1, 2, 3, 4, 5, 6, 7, and 8. So if we look at the second line, we're just setting things equal to each other, so that doesn't change anything. For line 4, we've got, okay, so we got to take the norm of VI. VI is a vector with, let's see here. So A is an M by N matrix. So V is going to be a column of this matrix, so it has N entries. So VI has N entries, and we want to find its 2 norm. So what you have to do is you have to take the dot, let's see here, so you can take each individual entry of VI and square it. And that will require N operations, because you take like VI1 times VI1, and then you take VI2 times VI2, and you have to do that for each entry, so you have to do N different multiplications. And then you have to do what? You have to add them all together. And so if you're adding N things together, you need to do N minus 1 separate additions. So then we've got N minus 1 flops. And then finally you have to take the square root of the final thing. And so there's another flop, and then so you add these together and you're going to get 2n. Okay, so that's how many flops you need for this particular row, every time you do that row, or that line of code. And by the way, it's a little ambiguous in the problem. I'm just going to say like addition, subtraction, multiplication, division. I'm going to assume they're all the same thing. I assume they don't want us to like ask like how many additions, how many subtractions, how many of each thing. I think that would be a little like unnecessary. That'd be a little much. But anyways, okay, so moving on to line 5, we take VI and we subtract a scalar. So for each entry of VI, we're doing a division. And so that's n separate divisions, and so we have n. Okay? Now moving on to line 7, Rij is, let's see here, we take the inner product of these two things. So if we think about it, in taking the inner product, that's sort of like what we did in 4. You have to take the dot product of 2, or here you have to like multiply 2 vectors together entry-wise. So that will be n operations, and then you have to add them all, which will be n minus 1. So we have n plus n minus 1, but here we don't have to take the square root at the end. So it just ends up being 2n minus 1. And then finally, here we set Vj. Okay, so let's think about this. First we have to multiply Rij by Qi. Qi has n entries, so we have to multiply Rij by each of those n entries, so that will be n of them. And then for each entry of Vj, we need to subtract Rij. Or we have to subtract the entry of Rij Qi. So I guess this would be plus another n. When I did this, let me see how I did this the first time. I did f and, yeah, 2m. Hold on, let's think about this. Oh no, I messed this up. Yeah, these are all supposed to be m's. Because it's an m by n matrix, so m is the thing that goes here. Wow, I really messed that up, and I am very sorry about that. These are vectors in Cm. Okay, that makes sense. Oops. Alright. M plus m is 2m. Okay, cool. Alright, so there we go. We've done the flop count of every single line. So let's see here. What am I doing in this problem write-up? Fi is going to refer to the number of floating point operations needed to perform the ith line of code. So let's see here. So blah, 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 blah. F8 is going to be 2m. That's good. Line 7 requires this thing. And so we're going to have 2m minus 1 for F7. Now line 6. Line 6 is going to be a loop in which line 7 and 8 are performed for every step of the loop. J in this loop varies from I plus 1 to n. And so if you're starting at line 6, then let's see here, how many different values of j do we have? If j is going from I plus 1 to n, then there's going to be n minus I different loops of this code. Because let's say that I is like 0. If I is 0, then you're going to have to do this n times. So it would be n minus I. Yeah. This is the type of thing where it's easy to be off by 1, but it turns out this is n plus I. And then for each of those loops, we have to do line 7 and then line 8. And so we take n minus I and we multiply by 2m minus 1 plus 2m, and that just becomes n minus I times 4m minus 1. All right, then we move on. Line 5 is just F5 is m. Line 4, blah, blah, blah. So we're going to assume that we're using the 2 norm here. Other norms might be different, I think. But we'll just assume we're doing the 2 norm. So then we have to do this thing, and as I talked about, this will give us 2m flops. And then finally, for F3, okay, well, lines 1 and 2, we don't have any flops. So the total number of flops that we do in this code is just how many flops we do starting at line 3, because lines 1 and 2 won't contribute. So if we start at line 3, then we do lines 4 and onwards n times. So we're going to do lines 4, then 5, then 6. And remember, 6 starts a separate loop, but we'll include that separately. And so we take this. We take the sum from I equals 1 to n of F4 plus F5 plus F6, because for every single line 3 is a for loop that goes from I equals 1 to n. And F6, if you look at the formula for F6, there is an I here. So F6 depends on I. It's actually a function of I. And so we need to actually write this as a sum from I equals 1 to n, instead of as just n times F4 plus F5 plus F6. But anyways, when you do this, you get this sum of this thing, then you do a little bit of algebra, and you get to this. But then from here, obviously the sum from I equals 1 to n of n is just, well, that's just going to be n squared. And then you've got this minus, and then you have the sum from I equals 1 to n of I. And if you remember the formula for this, or like if you don't, you can look it up. The formula for this is n times n plus 1 over 2. That's just a fact about sums. Okay, so that's that, and then you just take this and you just reduce it a little bit more, and we get to this thing, and therefore we've determined the total number of flops. And in fact, what you should do at the end of this is just check that this matches what you have in the book, because in the book that it says that like for n and m being large, the flop count should be on the order of m times n squared. And if we look at this, if we multiply this out, the highest order term is going to be this 4m times n squared over 2. That's going to be 2mn squared. So yeah, I believe in the textbook it is actually, on the order of 2mn squared for large m and n. But yeah, and that actually agrees with this. And in fact, when I did this problem the first time, I did not get that order of accuracy, and then I realized I had completely messed up a whole bunch of things, which is why I didn't do that. So it's good to have things like this that you can check to verify that the answer that you got is not complete garbage. And so this seems to check out, so I'm pretty sure that this answer is not complete garbage. And I've looked over this multiple times, and this seems like the natural way to do it. So yeah, there you go. This is the total number of flops required to run algorithm 8.1, and this completes the exercise.